Hi everybody, welcome back. And in this video, we're going to continue the topic of transfer learning, extending that to the concept of fine tuning. We're still going to load in the pre-trained weights for the convolutional base of the VGG16 network, but then we're going to make the last four layers of the convolutional base trainable so that the network is able to continue learning features that are more closely associated with hand signals, with the expectation that we will achieve a greater validation accuracy. Notice that the only difference between this approach and the previous notebook is that we're going to train the last few layers of the convolutional base plus the new dense classifier that we add at the end. So let's go ahead and get started. We have our typical system configuration, downloading of the dataset and configuration of the model parameters. And then, as in the previous video, we're going to instantiate the convolutional base of the VGG16 model with pre-trained weights from the ImageNet dataset by explicitly setting the weights argument to ImageNet. And also, like last time, we're going to set the argument for include top to false because we're going to supply our own dense classifier further below. So now let's talk about what it means to fine-tune a model in the context of transfer learning. If you recall in the previous notebook, using the entire pre-trained convolutional base produced a validation accuracy of 93%. This is pretty good, but we would hope to have a much better performance from a deep neural network. Referring to the figure below, the general idea is to instantiate the model with pre-trained weights from the convolutional base of the network, and then instead of freezing all of those weights, we're going to freeze the weights associated with the first several layers of the convolutional base, and then allow the last few layers to be trained along with the new dense classifier that we'll need to add. We can still think of the frozen layers as a black box feature extractor that's going to produce a useful set of lower level features, but then we are then fine-tuning the features in the later stages of the convolutional base to improve the model's accuracy for the ASL dataset. As we demonstrated in the previous notebook, we can use the trainable attribute of the convolutional base to either freeze all of the layers of the convolutional base or make them all trainable by setting the flag to either false or true respectively. But each layer in the base also has a trainable attribute, so this provides the flexibility to selectively toggle those individual layers. And therefore, there's a couple of different approaches we could use to freeze the first portion of the base and make only the last four layers of the convolutional base trainable. First, we could set the entire convolutional base to be trainable and then loop over the initial layers in the base to set their trainable attributes to false, or in reverse, we could alternatively freeze the entire convolutional base by setting the trainable attribute to false, and then loop over the last few layers of the base and set the trainable attribute to true. So either approach can work, and in this example below, we're going to use the first approach. So here you can see that we are setting the trainable attribute for the entire convolutional base to be true. And then in this next section, we're going to specify that we'd like to fine-tune the last four layers of the convolutional base. And so we're going to loop over all the layers in the convolutional base, except for the last four. And we're going to set the trainable attribute for those layers to be false, which freezes the initial layers to preserve the pre-trained weights from ImageNet, but still allowing the last four layers to be trainable. The code in the next section is identical to the previous video, in which we created a new dense classifier with a single layer of 256 nodes, followed by a softmax output layer with 29 nodes. So moving along, now that we're ready, we can prepare the data by creating a batch dataset object for both the training and validation. And then, as we've done before, we're going to use the trainable batch dataset object to display some of the images from the dataset. Now we're ready to compile and train the model. Since we've reviewed this process several times in previous notebooks, let's continue and take a look at the training results. As you can see in the training results below, the validation accuracy quickly rises above 90% and then continues to learn and eventually achieves the validation accuracy of 98%, which is 5% greater than in the previous notebook. So, fine-tuning the last four layers of the convolutional base yielded a 5% improvement. As always, it's interesting to take a look at the misclassified images to get a sense of where the neural net is being tripped up in the dataset. So as a recap, we concluded the topic of transfer learning in this series by showing you how we can start with a pre-trained convolutional base and then selectively fine-tune specific layers at the end of the convolutional base to learn a better set of features that are more relevant to the dataset of interest. This is the type of thing that typically requires a lot of experimentation, and we've only run through one example in this notebook. We showed how you could achieve a 5% improvement in this example, but we would encourage you to also experiment with data augmentation and fine-tuning to see if you could improve the results using both methods, and also to experiment with the different learning rates and also the number of layers that you decide to fine-tune. So there's a lot of ways to experiment to find the optimal results. In the next video coming up, we're going to briefly summarize the key points from the last 4 videos on transfer learning. Thanks so much, and we'll see you next time.